Do different substances have different values of delta nu, and if so, why is that the case? Could it be related to their unique molecular structures and vibrational properties? For a single given substance, does the Raman shift delta nu remain constant even if the frequency of the incident light changes, and what does that tell us about the nature of Raman scattering? Why is delta nu considered independent of the frequency of the incoming photon? Does this suggest that the shift is determined solely by internal molecular transitions rather than external light properties? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? Can we say that delta nu is a fixed, characteristic value for each substance, and if so, what makes it a reliable signature for identifying materials? How is delta nu connected to the vibrational and rotational energy levels of molecules, and what can we learn from analyzing this shift in terms of molecular dynamics? Is it accurate to say that the Raman shift provides a kind of molecular fingerprint, allowing scientists to recognize substances based on their vibrational modes? What role does this frequency difference play in qualitative analysis, and how does it enable researchers to distinguish one chemical compound from another? Can the same principle be applied to structural analysis, and how does examining delta nu reveal the internal bonding and arrangement of atoms within a molecule? Why is it important that the Raman shift is not influenced by the frequency of the laser or incident light, and how does this consistency enhance its usefulness in spectroscopy? Could we say that this property makes Raman spectroscopy a particularly robust and dependable technique in identifying materials even under different lighting conditions or experimental setups? How do scientists use Raman shifts in practical applications, such as identifying unknown substances, monitoring chemical reactions, or investigating molecular structures in fields ranging from chemistry to biology to materials science? Can you imagine why this precise measurement of energy differences reflected as a shift in frequency serves as a cornerstone for non-destructive and highly specific molecular analysis? What does Raman spectroscopy actually detect when it analyzes molecular vibrations, and how is this related to the concept of a change in the polarization rate of a molecule during a vibrational transition? What exactly is meant by polarization in this context, and why is a change in polarization rate important for Raman activity? How does this differ from what infrared IR spectroscopy detects? Could it be that IR spectroscopy is based instead on detecting changes in a molecule's dipole moment during a vibrational transition? What is a dipole moment, and why would its change be significant in identifying molecular vibrations through IR techniques?